So welcome again. So today I will use a mix of both this smart notebook and also a pre-made presentation. But the topics that I will cover today is first of all that I will go through what's called decision theory. And that is, in some sense, going a step backwards, in that what we have been discussing already is to say that, well, if we want to predict y given x, we are using then some f hat of x, which then should approximate the expectation of y given x. So we are, in some sense, saying that, well, we want to estimate the expectation, but why should we use the expectation? So we will see that that actually is optimal in some sense. After that, I will also discuss a bit about some general aspects with respect to prediction, in particular high dimensional settings, and also some other topics of generality, and that will be at the end of chapter 2. But I hope that I then will also be able to start on chapter 3, which then will be in particular linear regression. But in general, chapter 3 is about linear methods for regression, which includes linear regression, but we will see that there also are other type of linear methods that we will apply. That part will be partly some repetition of earlier courses, but then after we have had that repetition, we will also go further and see how we can actually do other things than just the standard linear regression setting. But let's start then with decision theory. And now we will consider a somewhat more general setting than what we have done so far, in that we will assume that we have this pair of x's and y's, both which are stochastic. So we will assume that they follow some distribution, which we just call p of x, y. And for simplicity, we now assume that both x and y are continuous, so they have some kind of density. In the book, they are doing it a bit more general, but it is sufficient to consider this in a continuous setting. And the problem that we want to consider is then how to predict y given x. So that's the setting that we want to. It was very large. Sorry. Let's see. That we want to consider. What we have then seen earlier is that the expectation of y given x is reasonable. But without giving any more formal basis for that this is a reasonable choice. And we will actually see that there could be other choices. But in order to formalize this, then decision theory is based on that we define what we call a loss function. And I should warn you that this now will be a bit more mathematical than many of the other things that we will discuss during the course. So we define a loss function, saying something about how we evaluate how bad we are doing. So this loss function is a function of the actual variable that we want to predict, which is y, but then also on the prediction that we make. So this is a way of measuring how bad we are doing. A typical choice is to say that this loss function is then y minus y hat squared. So that would then correspond to a squared loss, which is typically what people choose, partly because it's mathematically convenient, but also because it's a reasonable choice. And how does this look? Well, if we have then y here, and we have the y hat on the x-axis, this would then correspond to something like that. So, the worse we are doing, the worse is the loss. And this is, of course, a feature that we would like of a loss function. But note that there could be alternatives. An alternative could be to say that this Ly y hat is the absolute value of y minus y hat. So that would correspond to something like this. Let's see if I could make that. Oh, that was not good. Right. So that's an alternative, and it's not obvious which one to choose. But what we will then see, we will go through the mathematics on what this square loss function will result in, and then we will also just give results on if we have this absolute deviation instead. Okay, but in general then we have this this loss function L of y y hat. Well, a problem now if we want to, well, first of all, we want to minimize the loss. So, the smaller loss, the better. I should perhaps also say that this is this is typically from a statistician, in that we look in some sense at the negative part, how much do we lose. If you go, for instance, into econometrics, they're talking about the utility instead, which is just the opposite sign of the loss function. So they use u of L hat could be minus then L of y hat. So they look in some sense at more positive settings and how good can we do. But it's just then changing minimization to maximization. So it's just a different terminology. But as I mentioned, what we want to do is then to minimize now the loss. The problem, of course, is that we don't know why, because that's what we want to predict. So instead of then trying to minimize the loss directly, we are taking into account that we have some stochasticity. So there are some random variables involved. So instead, we minimize the expectation of the loss function. And we minimize it then with respect to y hat. So how and note that this y hat is then a function of x. So that's so now we have made a mathematical problem. How can we then minimize this expectation in a general setting, but also specifically then in this case where we have a square root? I just need to look a bit on my notes here. this square loss setting. Okay, but then let's now consider the specific case where L of y hat is then y minus y hat. And to keep the notation in the book, let's now say that y hat is some function f of x. So this means then that is y minus f of x squared. And then we want now to find the function f of x such that this expected loss is minimized. And this is sometimes called the expected prediction error. So in this case, it will be then the expectation of y minus f of x squared. And now we have to keep in mind what is the stochastic part here. Well, I started with was to say that, well, both y and x are stochastic. So this means that it's actually a double integral of y minus f of x squared times the distribution of x and y, which I call p of xy. So that's now the first part. But then what we are going to use is that we can always write p of xy equal to p of x, p of y given x. So it's the marginal distribution of x times the conditional distribution of y given x. Okay, but if we then insert that, we can now write this as the y minus f of x squared p of x, p of y given x, dx dy. Okay, but then we go one step further. First of all, we just switch the order of the integral. That there are some formal arguments for when one can do that, but those are typically satisfied in this setting. So we can write this now as an integral. So we just shift to dy dx. And then we have the integral of y minus f of x squared p of y given x. Yeah. And then, sorry, I should have, let's see if I'm able to erase. So, y and then, sorry. X dy, and then we have p of x dx. Okay, and so the task is still to find the optimal function f, which then minimizes this expression. But note now that then it's sufficient to minimize this part for each x. So instead of considering all x's at the same time, you could just look at one fixed x and then minimize then the expression inside the integral. And if we are able to do that for any x, then we have then the function that we need. So this means that we need to find f x, which is then the value, and I write this as the argument mean, the value, and let's call it c, which minimizes then this inner integral, where I now just put in a value c for f of x, p of y given x dy. So this is then the task then that we now want to minimize. Okay, but then how can we actually do this? Well, then we use a trick that we have used already, in that we can extract the expectation of y given x and add the expectation of y given x minus c squared, p of y given x dx. And then we can use this quadratic rule. So this will be then y minus the expectation of y given x squared p of y given x dx plus, so there should be a large parenthesis there, the integral of y minus the expectation of y given x times the expectation of y given x minus c squared p of y given x dx, and then plus the integral of the expectation of y given x minus c squared p of y given x dx. Okay, and then we have this final parenthesis there. Okay, but then let's look at the different terms here. If you look at this first term, so this one, we see that that doesn't involve c at all. So this is just a constant. So that means that we want to find the c which minimizes this. We can actually ignore that first term. So we can just remove that one. So then we can go on and look at the second term. And sorry, there shouldn't be a square there. And now, if you look at the expectation of y given x, well, the expectation of y given x, that is now just a constant for a fixed x. And c is just a constant, so it doesn't depend on, there should be an integral with respect to y all the time. Close that. So when we consider this for different values of y, then this term is again just a constant, which you can put outside the integral. So it's the expectation of y given x minus c times the integral of y minus the expectation of y given x p of y given x dy, and then plus And now if we look at this last term, we see still that c is just a constant. The expectation of y is now also just a constant given x, so that we also can put outside the integral. So that's the expectation of y given x minus c squared times the integral of p of y given x dy. Okay, but then if we now look at this first integral, so what is the integral of y times p of y given x? Well, that's just the expectation of y given. So perhaps I should go through that. So we have the expectation of y given x minus c, and then we have the integral of y p of y given x minus of dy minus the integral of expectation, let's erase that. Now this expectation of y given x is again just a constant which you can put outside the integral. So we have integral of p of y given x dy. So that was the first term. And then for the last term here, note that this last integral is an integral of a density, and an integral of a density is just 1. So we get then just the expectation of y given x minus c squared. Okay, but then if we now look at this, I don't know why I did got this, so sorry. Now, if we look at this integral, so this is an integral of a variable y times its density, but that's an expectation. So this is the expectation of y given x. So we have this first term again, y minus x minus c. And then this term is just now the expectation of y given x. And then if you look at this part, this is also the expectation of y given, oops, what happened there? There we go. This is also then the expectation of y given x times this integral, but this is the same integral as before, it's just 1. And then we get the expectation of y given x minus c squared. Now we see that this first term we have the expectation of y given f minus the expectation of y given x. That's just 0. So this cancels out. And the only thing that is remaining is this. Now, if we look at this term, we see that, well, because we have the square here, it's always positive, or large or equal to 0. But we can actually make it as equal to 0 by choosing c to be the expectation of y given x. So the actual optimal value is the expectation of y given x. That's the best value that we can actually choose. So, this then is a bit lengthy mathematical derivation to show that what we actually have been doing so far, and that we try to find this conditional expectation, is actually the optimal one. And how have I actually done this? Well, what we have done earlier, we have assumed that y is f of x plus epsilon, where the expectation of epsilon is equal to 0. And then we have that the expectation of y given x is just f of x. And this is the target. That's the function that we actually want to minimize or to estimate. And this decision theory is then an argument for why this expectation is a reasonable thing to do, or actually optimal thing to do in this setting. Okay, but then I'll just use this presentation a little bit. So what we have now shown is then essentially this. And there are different ways of estimating that conditional expectation. As we have seen, it could be by linear regression, it could be by the nearest neighbor methods, and so on. This was then when we had this specific loss function, this square error loss. So that's a specific choice that we make. Now, we could, as I mentioned, have alternative choices. So we could look at this absolute error instead, so y minus the absolute value of y minus f of x. Then we can go through similar type of derivations as we have done and show that in that case it's not the expectation anymore, but it's the median of this distribution of y given x that is the optimal value. Now, if we have a symmetric distribution, the median and the expectation will be the same. But if we have a very skewed distribution, they could be different. And sometimes one would prefer that median instead, due to that medians are often more robust than expectations. So it's in particular less sensitive to large errors. But it is mathematically less convenient in that if you try to go through this derivation and actually show that this median is the optimal thing, then it's a bit more tricky. So that's one reason why this loss, squared error loss has been quite popular. It gives more mathematical convenient results, and also it still is reasonable. Now, there is a similar theory for classification. In that case, we are not predicting a continuous response, but rather predicting a categorical response. And we will actually go through that part as well, but I will skip that for now and leave it until we get back to classification more thoroughly. So even though it's given now in this presentation, I will just jump further. So what I also then want to discuss then from chapter 2 is then two extra issues. So this is a quite separate theme from this decision theory. So what we have seen then is that we want now to estimate this conditional expectation. So that's the optimal thing to use if we want to predict with this square error loss function. If we have classification, actually we need to find the class that has highest probability That would be the optimal in that case. But let's concentrate on this expectation. Now, to illustrate that things can be very difficult in high dimensions, let's look at then some one method, which is we call a local method or a nearest neighbor method. So we have seen this way of estimating f hat earlier, in that we look at then an average of responses nearby the point x that we are interested in. So that's a reasonable way of doing it. And the typical choice is then to say that, well, we include those, well, there are two typical ways. One is to say that, well, we make a restriction in that we say all points that are closer in distance to x closer than a value e, we include. That could be a pre-specified value e. The alternative that we have seen is to say that, well, we take the 10 closest points or the 15 closest points. But let's look at this setting. And for simplicity, let's assume now that all the x's are in the cube. So each component is within the interval 0 to 1. And we have p of those. So we have a cube to the power of p. Okay, but let's assume now that we want to include or specify the e such that actually a fraction, let's say 5% of the data, are included in when we take this average. Now, if we look at one dimension, then this e could be quite large. But if we include it to 2, then we need, then the e could be quite small. But if we increase the dimension, what happens is then that actually the e that we have to choose increases quite a lot. Now, this is perhaps not that easy to see on this plot. So let's go to this setting. This is a more specific setting. So let's assume that we have one function, f of x, which is then the exponential of -8 times the distance of x to origin squared. And we want to estimate it by then the one nearest neighbor. So we take the nearest point. How close will that point be now in a cube again? But we have changed it a little bit just to make it symmetric. So now the cube is going from -1 to 1. So in one dimension, this function looks like this, well, something like a Gaussian distribution. This is almost a Gaussian distribution. But let's assume now that we have actually observed these green points. And these are illustrated in 2 dimensions. But let's first look at the setting where we just have one dimension, so only x1. And we want then to look at how large can this distance be before we actually get the first point. And that would mean then to increase an interval. So for simplicity, the point we're interested in is x equal to 0. So we increase an interval around 0 until the first green point is included in the interval. And that corresponds to this interval here. And then we see that the distance is not that big in this case. But let's now assume that we go to 2 dimensions. So now we include x2. In that case, when we again want to look at the nearest point that to this 0, 0 point, in this case, we need to look at a circle. Increase the circle until we get the first green point included in the circle. And this blue circle is then the solution in that case. Note that actually the distance in this case is larger than in one dimension. So when we go from one dimension to 2 dimensions, we actually need to increase this, this E that we had on the previous slide. And this gets worse and worse when we are increasing the dimension. So here we then see how the average distance is given in different dimensions. So it's quite close if you just have one x variable, but then it increases as the dimension increases. And look, note that when p is equal to 10, it looks like we're taking a distance of approximately 1, but that would include all x's. So then we are actually not able to do this nearest, not including all the x's, include the whole space. So that means that it's not very local anymore. So this is then a problem that we have when we are dealing with prediction, in that when the dimension of x, the number of x's increases, it becomes more and more difficult. And this is something that we have to keep in mind when we are going further. Right. I think actually now, let's see how we're doing with time here. That I will now go on to chapter 3. But perhaps I should stop. It will be a bit more, a bit easier now actually to follow compared to what we have done so far. So let's see. So chapter 2 actually then discussed prediction and also classification in a very general setting. What we are going to do then in chapter 3 is an easier task, in that we will narrow down the possible ways we are estimating this f function to linear settings. And this will then partly be a repetition of topics that have been considered in earlier courses, but there will also then be extensions of that. So what we are going to do is then to go through what linear regression is, and we will look at some properties. But we will also then discuss some challenges related to, and in particular weaknesses related to then these methods. And then that will be used as a motivation also for more advanced methods. We will make it somewhat practical, in that we will illustrate it through one of these examples that we have seen earlier, where it's a quite simple example where we are interested in a numerical response, which is then the amount of sales of a specific product in different markets. And where we have then 3 explanatory variables, and that are different types of advertisement made, either in TV or radio or in newspapers. And we did look then at these plots earlier. This shows then the 3 different plots shows then the explanatory variable on the x-axis, and then the response variable on the y-axis. And as we discussed earlier, this is a data set where linear methods could do reasonably well. But there are many questions that we then can pose in this setting, in that first of all, given that we only have the data, can we actually say that this relationship is linear, or is it something else? And how strong is the relationship? It looks like it's stronger, the relationship between TV and sales than newspapers and sales. But if you look at all the three axes combined, how strong is the relationship then? It could be interesting if we have a limited budget, we might be wanting to optimize how we use those money on advertising. Is it so that we should put everything on TV and just forget all the other things? Or are there something else that is better to do? And then also it could be interesting how precise can we estimate the effect and so on. So many different questions that we would like to pose here. Okay. So this is now a slide just showing what we have been through earlier. So what we do now is that we make a model. So we have data, a lot of x's and y's from 1 to n. And we make now a model saying that the y is built up by a linear relationship of the x's, but this relationship is not perfect, so we have some noise in the end. And so far we'll just assume that this noise has expectation 0 and variance sigma squared, and they are all independent. So we are not assuming that they are Gaussian so far, so that's why there is not an n in front here. This notation just means then that we specify that they are all have expectation 0 and all have the same variance and independence. And then we saw earlier as well that we could write this relationship in matrix form by specifying this design matrix and corresponding vectors. And then we have this on vector form y equal to x beta plus epsilon. And then also we saw that the least squares estimate is then given by this beta hat, which is then has this analytical expression. And based on this, we can then predict a new point at a new point x star by just using then y hat by inserting then the estimates of beta into this, and then note also that we in some sense predict also the epsilon to be 0, because we don't have any more information on that. So that will then be the setting that we will consider. Okay, but then, and I think I could just continue with using this presentation here now. In order now to say something about the properties of the estimates of beta hat and so on, we need to introduce some mathematical terminology. First of all, we will talk about random vectors. So we have in earlier courses talked about random variables, but we will just generalize this now to vectors. So and it's in some sense an obvious extension, in that we say that if now we have a set of random variables, set 1 to set p, then if we make a vector of those, we call it a random vector. So it's not more complicated than that. But then we will go further and also define expectations and variances of such a vector. And the first part is again quite easy, in that when we talk about an expectation of a random vector, that is just the vector of the expectations. So it's the expectation of set 1, the expectation of set 2, and all the way up to set p. So that is then the expectation vector. But then when we want to now generalize variance, it is a bit more complicated, because now we not only want to say something about variances, but we also want to say something about covariances. And we structure all those ingredients in a matrix, where at the diagonal we specify the variances for each of the p variables. So the first component here is just the variance of set 1, variance of set 2, and so on. But then on the off diagonal, we include the covariances. So element 1, 2 will then be the covariance between set 1 and set 2, and so on. So this is just a way of summarizing then the first and second order properties of these random vectors. Okay, let's see. Need to break soon. Yeah. Okay, so what we are going to then do then after the break is to talk about some rules that we that we have on expectations and covariance matrices of vectors, and then we will use that to say something about the properties of these beta hats that we have looked at earlier. But let's take then 15 minutes break, so then we could start perhaps 17 past 11.